3. Okay, so in this video, what I'm going to be doing is I'm going to be talking about shear, right? Now, shear, we can define shear as whenever we have, so if we have a beam, right, we're going to learn when we do beams and bending, maybe you've already seen that, but a perpendicular force causes shear. Now, Copeland in his notes goes into quite a lot of detail about how that works, but what we can imagine is that if we take this part of the beam, effectively we have a force pushing down, and then we need something to resist that. So it's going to be the steel is going to be pushing back up. This steel next to it is going to be pushing up. And what we can think of is every layer of this beam, every perpendicular layer being another section which is trying to resist slicing. So shear is failure where perpendicular layers of material slide past each other. If you had to give a definition, shear is when perpendicular layers slide past each other due to parallel layers slide past each other due to a perpendicular force. Okay, if we need to find shear stress, well, shear stress is the same as all the other stress formulas. It's going to be stress equals force over area. But I'll tell you the problem a lot of people get, and this is why we sometimes include the little S for shear, or V for shear when you get to uni, is that if we have this situation here where I'm trying to punch a hole through this plate of steel, is that what we imagine is, a lot of the time we imagine that when the punch is being applied, so this is a punch, when it's being applied to the solid surface, is they just imagine it's being compressed. And that's not what's happening. We're not squashing the piece of metal until it fails. What we're trying to do is we're trying to cut this piece out. So we're going to have a piece that pops out at the end of it, which is perfectly cut. It's not going to be compressed. And that's a big distinction. A lot of people don't appreciate the difference between cutting and squashing. So when we talk about shear, we're cutting with parallel layers sliding past each other due to a perpendicular force. So we're not going to be compressing. Now, when we do this area, with compression we're interested in cross-sectional area, but with shear, we're interested in a different area. What I call here, so we have two different main fields of shear. So what we have here is we have punching shear, where we're going to punch a hole or shape out of material. And the thing that most people are familiar with is anyone who's ever made cookies, right? Cookie dough, you've used cookie cutters, so think of it like gingerbread man, right? If you use a gingerbread man, it's got a cutter, right? That's my gingerbread man. It's not ideal, but it will do. I've got a cutter, and what it's going to do is it's going to cut out that material. It's not squashing the entirety of the material, it's just cutting through. Now, what we are interested in is we're interested in an area. We have force over area. So this line is a perimeter. To get the area, what I like to think of it as, I like to think of it as ribbon shear. So in this case, I like to think of it as, imagine a ribbon or the label of a tin, that sort of thing, but I call it ribbon because that sounds good. And it looks to me like a ribbon. So if I have this area here, I want you to imagine that it's a ribbon, and that is the area that we're cutting. So in this case, let's look at this question here. What we're going to do is we're going to find the area. We've got the force, we've got the diameter. What we need to do is find the area. So in this case here, our area is going to equal the circumference, and circumference is equal to pi times diameter. So pi times diameter times the thickness. Now thickness we can write as T, or H is often used for height. So we're going to use pi dh as our formula here. We're going to I'm going to switch this pen just so I can make sure it's picking it up clearly. This one's usually pretty dark. Okay, so in our case here, what we're looking at is area is, oh, that's green. We'll stick with black. Okay, so area is equal to 3.14 times, someone got a calculator, you can type this in, times 30 times the thickness of the material, which is 20. And that will give us, so it's going to be 600 pi. 600 pi is going to be times 3-ish, it's going to be 1900. Okay, now I like to use...
1884.
Sorry, what's that?
1884.
1884, and that's in millimeters squared. Now I'm quite happy to keep millimeters squared. The reason I'm happy to keep millimeters squared is because I know from grease units we go together like megapascals and millimeters squared. So we're going to use that. And so in our case here, we can now go to our force, which is 60. Now, newtons are not in the song, right? They're not the Greece units. So that means we have to convert it back to its base units. So we're going to write 60,000, or 60 times 10 to the 3, divided by 1884 equals... I just don't have as much room as I'd like to show that on the board. Calculator?
Yes.
Oh, okay. What are we entering?
60,000 divided by 2,000. So it's going to be about 30?
30.
Well, it's not. It's going to be close to 30.
Oh, but yeah. 31.8.
Excellent. Okay. So I just don't have quite as. I'm going to go to this part of the wall here, and I'm going to say 31.85 megapascals. Yeah, because I used millimeters. That gives me my answer in megapascals. Now I'm pretty sure Copeland does it a slightly different way, but so he breaks everything down into meters. I'm happy to use this method. He's got 31.9. Yep, that's great. So we've finished our first one. I'm just giving myself a little bit more room for the next one. That's a shame. I wanted that picture. Oh well, those of you who are watching this on video, you can go back to see that picture when it comes up. Okay, so we're going to go down to this one now here. In this case, we are punching not just the hole, but we're actually punching this shape out of a piece of metal. We're cutting the perimeter as well. Yeah, so we're going to punch the whole thing, including the hole, in one part. So in this case, let's have a look at the area that's being cut. So we'll say that our shear stress equals force divided by area. And our force, they haven't given us force in this question. So they have. A rectangular plate is being cut for a force of 60 newtons. Okay, 60 kilonewtons. Okay, so what we need to do is we need to find the area again. So in this case, the area is going to equal, we've got the area of the circle, which we said is going to be pi times 25 times the height, or the thickness, which is 10. And so we've got two of those. We've also got the perimeter of the plate, which is, the perimeter of this plate is 150 plus 150 plus 120 plus 120. You're okay with that concept? So it's going to be 2 times 150 plus 120. Okay, so what we're going to get here is, because we've got two circles, our area is going to equal 2AC plus AP. I probably should actually do the working out above first. Okay, so this is going to be 250 pi, 250 pi equals 785, and then this one is going to be 270 times 2 equals 540. So I'm going to multiply this one by 2, so our total area is going to equal 875 times 2 plus 540. So 785 plus 785 equals 2,100 millimeters. It's millimeters squared, of course. And then our force is, so stress equals force, which is 60,000 divided by 21, which is going to be pretty close to 30 again. Total perimeter. Five four. This is a very big perimeter. So I've done something wrong here. This is a very big perimeter, because this perimeter, the area of these two the perimeter of these two circles should be smaller than that one.
The diameter.
Here's what we did. We didn't multiply this one by the thickness.
Don't forget to smash that.
Okay, perimeter. So it's 10 times that. So we multiplied 10 here. We multiplied 10 here. So this is going to be that number. Great. Okay. 785 times 2 plus 5400 equals 6970. 6970. 61230 zeros divided by 6970 equals 8.61 megapascals. Yep, so we've got the same thing. Okay, good. So the next one we're going to go on to is we're going to look at, in this case, what I call bulk shear. So when I talk about these two kinds of shear questions, we have ribbon shear and we have bulk shear. Unfortunately, I rubbed out the picture I had earlier. I can maybe draw it up really quickly just to give you the concept. We don't need this one anymore. I'll leave that one just in case. So the idea is if I've got a piece of steel, and then here I have a bolt that's holding on. I can't really see anything else, but that'll do for our drawing, right? That's isometric. This is in section, right? What our section looks like. We have 3 pieces here. Now, how I like to think about this concept is I like to think about what direction are we going as we move through this diagram. So here, we're going left, 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 right, 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 left, 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 all the way down. So that might be familiar to some of you. So the idea is that at this location, we're going left and right. What we have is perpendicular forces. Now when I say perpendicular, it could be at an angle, in which case we're interested in the perpendicular component. But perpendicular forces causing parallel layers of material to slide past each other. Now, what is the area of material that is being slid past here? What kind of shape is it going to look like? Circular, right? It's going to be the circular section, the cross-sectional area of the bolt. What makes these questions interesting, though, is that if we have multiple pieces of steel, right, in this case we have double shear. That means we have 2 circles that we're calculating. Can you see the blue pen better, more easily than the black pen? Do I keep going with blue?
Oh, what's the same?
I will say that it's a Boardmaster.
Hey. Yeah, actually it looks much better.
Well, we'll stick with the blue. Okay, so what this diagram looks like, what we're seeing here is double shear. There's different ways that we could get shear. So we could have, if we just simply have one piece of material, let's say our tow bar, and then we have our hitch that didn't even smudge too bad. Okay, in this case that's single shear, right? We can also have triple shear. The number of shear depends on how many changes of direction. So in this case, if we had our bolt, it was going through here. In this case, how many changes of direction we have? Here, left, 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 right, right, right. So it's one change. That's single shear. Here we go, left, 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 right, 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 left, 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 right, right, right. How many changes did we have? Well, we have a change 1, 2, 3.